Good morning, everyone, and welcome back. It's my pleasure to chair this session. My name is Ingo Kurt. I'm a human geneticist, and today we will also have talks which cover topics that are crucial in human genetics, but also a broader topic. Because what is really important is to find the right diagnosis. And as we also heard yesterday, sometimes it can take a while before it comes to the right diagnosis. We heard that from TJ and his, well, let's call it a challenge before he got his diagnosis of Crohn's disease after 7 years. So we definitely, as humans, need help. And nowadays, that means we can also get help from computers, from machine learning programs, from AI. And it's my pleasure to introduce Tzung-Chien for the first talk on Gestalt Matcher, which is he will tell you better than I can, an image-based approach to improve diagnoses in rare disorders, so in monogenic diseases. The floor is yours.
Sorry, I'm looking for my slide. Here. Okay, great. Thanks for a kind introduction. So I'm Tzung-Chien Hsieh. First of all, I would like to thanks for this great opportunity to share my work with you. So today I'm going to talk about the next generation phenotyping for the rare Mendelian disorder. So the next generation phenotyping in this presentation is mainly about the facial analysis. So I would like to introduce how we utilize the facial analysis to help the diagnosis for the rare disorder. So there are two main parts in my today's presentation. So first of all, I would like to introduce how we utilize this facial diagnosis to diagnose the patients with the rare disorder. And the second part of my presentation, then it is about the medical image database for the rare disorder. So we call it the Gestalt Matcher database. Then I will introduce the current status of this database and also what we can do with this database. Okay, so first of all, you might wonder why we can diagnose the patients by looking at their face. So you might already notice that this is 3 patients with the Cornea de Lange syndrome. So you might already notice that there are some patterns shown in their face, so which is their eyebrow. So sometimes their eyebrow will even be connected. So therefore, we know that we can learn the facial representation of the disease by training on patients' photos and further help us to diagnose the patient. So for example, here we first train the deep convolutional neural network by thousands of patients' photos to learn the facial representations of the disease. And further, by analyzing these photos, then we can quantify the similarity of these photos to the 4 syndromes we train in the network. So in this case, the highest similarity is the Cohen-Cyrus syndrome. So we can further check the mutations related to Cohen-Cyrus 1 to further diagnose this patient. So the NGB technology has already significantly progressed in the last few years. So from 2014 to 2019, the training scale has increased from 8 syndromes in the Ferry paper to over 216 syndromes in Guroev paper, which is running behind the Face2Gene platform. So this method described in this paper is also called deep Gestalt. So I will use this term to refer to this study in my following presentation. And later in 2022, this year, we published the Gestalt Matcher approach in Nature Genetics. So this method is considered as the extension to the deep Gestalt approach. So it enables the analysis on the patient level. It also pushes us moving from classifying the disorder to discovering the novel disease. So first of all, I would like to start introducing how deep Gestalt works. So how deep Gestalt can diagnose the patient by looking at the face. So because we don't have a huge data set to train our model, so first of all, we need to use the technique called transfer learning. So we first train our deep convolutional neural network on the 500,000 healthy individual from the CASIA web phase to try to classify the different person. So for example, here we try to learn the general facial feature to distinguish between the Angela Merkel and the Frankenstein-Meyer. So then we first know how to distinguish the different person. Then the second step is that we replace the last layer. We try to distinguish different disorder. So for example, here we replace the last layer by the different disorder. And originally, the last layer is the different person. So here we further train the network by around 21,000 patients' photos and with around 300 disorders. So by these ways, then we can train our network even though we don't have a very, very huge data set. And this technology, Deep Gestalt, is already running behind a very well-known face-to-gene platform. So it is used by thousands of clinicians in their daily diagnostic workup. So however, although it is so powerful, so we still have lots of limitation to the rare disorder. So for example, so here we know that we are analyzing the rare disorders. So we have a very imbalanced distributions for the disorder. So here I would like to visualize how imbalance of our data set. So here is the distribution of the disorder, and the y-axis is the number of pathogenic submission in ClinVar. So if the submission is high, it means that we have more patients for this disorder. So it means that on the left of the figure it is the more frequent disorder, and on the right of the figure is more ultra-rare. So for example, here we have the KMT2D on the very left end. So we have around 354 pathogenic submission in ClinVar. And however, for the LEND2 gene on the right, we only have 2 submissions. So here we can see that so we have a very, very imbalanced data set. More than half of the disease-causing genes, we have less than 10 submissions in ClinVar. So because the artificial intelligence is just like a human, we need to learn the photos we need to learn the disorder from the photos. So if we don't have the photos, and then we are not able to really learn the photos very well. So not able to learn the disorder very well. So for example, for a Deep Gestalt phase 2 gene, so it can learn the disorder on the left-hand side very well, but for the disorder on the right-hand side, because we don't have too many photos of them, so we cannot really support the disorder by the Deep Gestalt approach. So the current limitation for the Deep Gestalt approach is around 7 patients. So therefore, here we want to propose the Gestalt measure approach as the extension to Deep Gestalt. So first of all, we aim to support more ultra-rare disorders and push our limit to the long tail on the right. And secondly, we want to increase the scalability. So for example, if our model is originally trained on these 4 syndromes, the Noonan, Cohen-Cyrus, HPMS, and Kabuki, but maybe tomorrow there's a doctor came to me and said that, hi, could you help me to support another disorder, maybe it's called LEND2 syndrome. So then I need to spend a few hours to retrain the model and reevaluate everything, then deploy the model in a website. And maybe next week, another doctor come to me and say that, could you help me to add another syndrome? Then I need to redo it again and again. So in this Gestalt measure approach, we want to increase our scalability. So we don't need to retrain our model to support new ultra-rare disorder. We want to be more flexible. So in the end, the clinicians are always looking for the similar patients. Therefore, we want to also be able to quantify the similarity between the patient, so which can help us or help the clinician to find the similar patient to their patient. And also, we can explain the relationship between the patient or between the disorder that could further help us to facilitate the lumper and splitter analysis. Okay, now I would like to introduce how we extend the Deep Gestalt to Gestalt measure approach. So the upper part here is just like what I introduced at the beginning. So this is just like the Deep Gestalt approach. So here is like we we try to train the deep convolutional neural network to classify the disorder. And in the deep Gestalt approach, there are two components, which is the feature encoder and the classifier. The feature encoder is to learn the facial feature, and the classifier is try to classify the facial feature into the disorder we train in the network. So how we extend this deep Gestalt to Gestalt measure approach is that we take the fully connected layer in the feature encoder, so the last fully connected layer in the feature encoder to span as a feature representation vector. Then we use this feature representation vector to span another space called clinical phase phenotype space. So this space, we have a 320-dimensional, it's a 320-dimensional space, and each photo or each patient is a point located in this space. Therefore, we can try to calculate the distance between the patient or between the photos in this space to quantify their similarity. So by this way, we can classify around maybe 1,000 syndrome or 2,000 syndromes in this space. We are no longer to restrict to the original, maybe around 300 syndromes we train in the network. And moreover, we can also quantify the similarity between the patient. We can further perform the clustering analysis or we can support more downstream analysis with the Gestalt measure approach. So just to summarize, so on the difference between these two approaches, the upper part is the deep Gestalt approach, which is running behind the well-known phase screen platform, and the lower part, which is our Gestalt measure approach, is the approach we published this year. So, and in this phenotype space, the similarity between two patients can be quantified by the cosine distance between two patients in this space. And moreover, so by projecting the patients from the high-dimensional 320-dimensional space down to the two-dimensional space, which is the figure shown on the left, we can see that the patients with the similar phenotype will cluster together. So therefore, we know that the patients are if the patients are close in the space, then they do have the similar facial phenotype. And then how we evaluate the performance. So this is the patients, so for example, this is the patients with the cophan. So how we evaluate the performance is that then we put these patients into the space with the other patients, maybe 1,000 syndromes, the other patients with another 1,000 syndromes. Then we calculate the distance between this patient and the other patients. Then we can further try to rank the distance by, rank the patient by the distance. So for example, here, the nearest patient in this space is also cophan. Then we can call it type 1 match, because this is the nearest patient. And this is another example, which is the Noonan syndrome patient. So if another patient with the Noonan syndrome is in the top 5 position or better than top 5 position, then we will call it top 5 match. So by this kind of evaluation, we can predict the disorder, and we can also predict on the patient level. Because if we aggregate the patient by the disorder, then we can predict the disorder, so just like phase 2 gene. But if we don't aggregate the disorder, then we can give a list of patients. So it can be just like we can provide a list of patients, then you can try to find the similar patient, whether that is similar to your patient, to the patient you want to analyze. So therefore, because we can provide a list of patients, so you can also think of like Gestalt measure is a facial image version of the gene measure. So you can upload your photos, then try to find the similar patient. And then, so for example, in the past, so usually the doctor will go to the dysmorphology meeting and to show a patient, say like, oh, is there anyone who also see this kind of patient? And then the doctor contact to each other, then try to publish the paper after the meeting. So if we have this kind of approach like facial image version of gene measure, so then we can upload the photo, then you will later receive like the email notification, this is similar to your patient, and this is the contact information of these clinicians. Then you can just try to discuss further, then try to publish another novel disease gene. Okay, so else we can also do for this downstream analysis? So here I would like to present another disease genes with around 440 photos from 40 different patients. So what we want to do is that sometimes we want to know that they look like a little bit similar, but how do we quantify the similarity? So for example, so first of all, this is the analysis done by one of our PhD student, Hannah. So I just help her to present the results here. So how do we say that these patients are similar? So first of all, what we do is we are trying to quantify the distance between the patient. So what we do is that we try to try to plot the distribution of the distance. So the first thing here we want to show is the blue one. So the blue one is the distance between the patients with the same disorder. So for example, we randomly select 10 patients of Cornea de Lange, then we calculate the distance between them. Or another point here will be randomly select 10 patients of the Kabuki syndrome, then we calculate the distance between them. Then we plot the plot the blue distribution. And we want to plot another distribution, which is the random selection. So for example, we randomly select 10 patients or 20 patients from around 300 disorders. We just randomly select them, and we try to plot the distance between them, so which is the red distribution. And now we want to compare our gene X to this randomly select distribution and also the same distribution, which is the green one. And also the black line here is the threshold between the same and the random selection. So here we can see that the gene X is just really right on the threshold. So they are around like the 50% of the combination is below the threshold, but also around 50% is above the threshold. So we cannot really tell that whether this is significantly similar or not similar. So then we further want to look into like the subcohort, and we want to identify whether there's a substructure inside this gene. So first of all, we found that there are a few patients are very similar, which is in the protein domain 1. So because I cannot tell you which domain, and also I cannot tell you which gene, so that's why I use gene X and domain 1 in this presentation. So here we can see that so the patient in this domain are more similar, so compared to overall the old patients. And also in the statistical analysis also tell us that this domain, the patient in this domain also show a significantly similarity compared to the other patients of the gene X. So therefore we try to so therefore the results show us that so this gene X maybe is only partially similar. So because what we want to show is that it's not just like binary answer, like yes they are similar, no they are not similar. We would like to provide like a level of similarity. So for example, here we will just maybe report this gene is partially similar, and we will also further report that the patient in the protein domain 1 is much more similar. And it is also enable us to do more analysis to correlate the molecular mechanism. So for example, we can analyze the patients within the same protein domain, and also we can analyze the patients with the similar mutation, for example, maybe the missense mutation, loss of function mutation. So we can do more downstream analysis. Okay, so go to further, sorry. Okay, so I would like to show another example is the cohort of gene Y. So here we have 33 photos from 32 patients. So these 33 photos are distributed into 2 exons. So in the first exon, we have 10 photos, and in the second exon, we have 23 photos. And also, we just wonder whether these 2 groups of patients looks different. And then we are trying to do the facial analysis on these two groups. And so that's why we perform the Gestalt matrix analysis. So here in this pairwise matrix shows the similarity of them. So if the color is darker, then it means that two patients are more similar. So the patients are sorted by the genomic location from the left to the right. So there is a boundary in the middle, which is here is the exon boundary. So on the left is the patient in the exon 1, and on the right is the patient in the exon 2. So here we can see there's a clear cluster. So which is on the left is a cluster 1, and right is the cluster 2. And also it also correlates with the molecular mechanism. So for example, so the patient on the right, which the mutation will cause the escape from the nonsense-mediated decay, but the patient on the left, which is in exon 1, so will not escape from the MND. And we further want to see more visualization, so we use the t-SNE, try to plot the 2D visualization. So in this case, we can see that so the two groups are totally separated into two parts. So the the blue one is the patient in the exon 2, and the orange one is the patient in the exon 1. So therefore, we know that the facial analysis tells us that so the patient in these two groups looks significantly different. So therefore, we can further split this disorder, this phenotype into two disorders. So we can prove that this disease gene is the pyatropy gene. Okay, so our Gestalt matrix approach currently already analyzed around 12 novel disease genes, and 4 of them already published in the journal or the Med archive. And here I would like to point out the first publication here is published by Maria. So this paper or this collaboration is established in the last year in the AGD meeting. So I'm also expect that we can continue publish more paper after this meeting today. Okay, so what we can do more about our Gestalt matrix analysis. So yesterday, my supervisor contacted me because he found a very interesting patient, so he would like me to show this patient here today. So this is the patient, and this is the photo, and also some of the clinical description. And so he just asked me, like, could you compare this patient to the other, like, Cornea de Lange patient, because I feel maybe this patient has this disease. So how do we do it? So usually we need to read a lot of papers, so to collect the photo, to collect a lot of information. So originally what I want to do yesterday is like, I want to go over all the papers of Cornea de Lange. So for example, like this, there are a lot of photos here, and a lot of photos in another paper. And also there will be a huge table like this, lists all the information like the variance, age, or the gender. And in the end, I might need to read through the whole paragraph like this to collect the HPO terms. But because my supervisor contacted me yesterday at 11, so I don't really have time to do it. So how do I do it in the end? So I called our medical student to say, could you help me? But she said, it's too late. So, but you are lucky because I read the paper a few weeks ago, and then I put them in the database, which is called our Gestalt matrix database. So our curators already put all the patients with the Cornea de Lange in the database. So for example, these are the patients with the Cornea de Lange, and there's photos here, then, so I don't need to collect photos myself. So I can just use this database to do the literature research. And then, so what is this database? So the Gestalt matrix database is the medical image database for the rare disorders. So there are around more than 10,000 images from 7,400 patients. And we collect these patients from over 2,800 publications. It's already covered around 700 different disorders. And this And this database is hosted by the AGD, and AGD is a nonprofit organization in Germany. Okay, maybe I stop here because you might know better than me about this organization. Okay, so this database contains a lot of different images. So for example, we have like the facial photos, profile, and also like hand X-ray images. And we also collect like fundoscopy images and also like the photos from the limbs and so on. And moreover, so we don't just collect the photos from or the patients from the publication. So this, we also enable the worldwide collaboration. So there are around 300 clinicians already contribute the patient. We have around 150 unpublished patients, and then we have around 7 different patient support groups. And currently we already published 4 papers, and there are 8 papers still under revision. So in this database, we don't store only the image, we also store the age, ethnicity, gender, and the privacy setting. So here you can use as the public setting and or the private setting. If it's public, then everyone in this database can see it, and if it's private, then only you will see this patient. So also we store the information like the PubMed ID, DOI, and also the corresponding author, which can be used to contact to each other. And moreover, what we can do is that we can perform the Gestalt meta-analysis. So here we want to compare this patient to the other Cornea de Lange patient. So here we can see that on the right, which is the pairwise comparison matrix. So this patient is totally different from the Cornea de Lange, just from the color code and also the clustering dendrograms. So then maybe the Cornea de Lange is not the right diagnosis, then we can check the other diagnosis later. So moreover, the Gestalt measure database can also serve as the medical, also the database to store the images. You can also use this database to cite in your paper in the medRxiv, because we know that we cannot show the photos in medRxiv. So you could also first of all put the photos here in the Gestalt measure database, then further put the link in your paper then you can use it in the medRxiv. Okay, in the end, so this is the most important slide in this presentation. You can forget everything before then, but please remember this one. So because we know that the patient and the database is the most important thing for this AI study. So if we have the data, then we can do a lot of analysis. So now, that's why we want to start this global collaboration. So we are trying to collect the unpublished patients for the disorders. Then we will have more data. We can do more analysis. And moreover, so the clinicians can also use this database as the modern version of the London medical dataset. They can also browse the images to learn the disorders. So here we are trying to collect the disorder like the Noonan syndrome, Soto's, Treacher-Collins, Stickler syndromes, or any other disorders. So if you have this patients, so please feel free to contact me. Then we will include you in our Gestalt measure paper. Okay, in the end, so I would like to thank everyone who contributed to this study, and I would like to thank our colleague in IGSB and also Translate NANSA project, and also everyone who contribute to these studies. Thank you.
Yeah, thank you very much. It's really a great database, and we have time for 1 or 2 questions. Joachim.
Yeah, super. Thank you very much. Always excited to see how fast this goes forward in your project. I might have missed it. How do you make the decision whether a genetic mutation that leads to a syndrome might be seen by this approach or not? I mean, there will be genetic mutations and diseases that might not have any impact on the face. So how do you make that call? So
I think, so here maybe there are 2 steps. So the first step is that we need to know whether this patient has the facial dysmorphism, because the Gestalt measure is analyzing the facial dysmorphism. If this patient don't have anything shown in the face, then maybe it is not really suitable for this analysis. So I think this kind of analysis can be two-step. The first step will be like, I want to measure whether there's a facial dysmorphism present in this patient. If there is, then we can go to do the Gestalt measure analysis.
Yeah, good. Your question. Yeah, cool, really cool presentation. Also, I guess, really promising for many diseases we are working on. My question is, just for my own education, how does it work with different age groups? That I could imagine, many of you showed many children. That's also typically what I think who comes to the clinic where you have these images. Can you, if you have people from the same syndrome, and you have one which might be 25 years old, is your algorithm already strong enough to match that individual then to this group, or is it then somehow matched to older individuals, not to that syndrome anymore?
Yeah, so I think this is a very, very important question. So, and I think this is also the main criticism to this kind of analysis. So, because as you already mentioned, like the majority of our data is from maybe the young generation, like maybe the patients under 10 or maybe even younger. So sometimes we know that for older patients, so maybe the prediction is not really well because it's all trained on the young patient. So that's why, and I think we have another. So we also provide another analysis try to remove this confounder. So for example, we can use the GAN approach. We can have another classifier, which is classifying the different age, and the main classifier is classifying different disorder. So we try to have the feature. We try to learn the feature vector that is not suitable to classify the age, but suitable to classify the disorder. But I think the final goal will be like we want to collect the database or collect the data with more older patients. So I think maybe this could be also a very. You could also have more information in our talk, one of our talk in the afternoon. So I think Dr. Solomon will also present some of using the GAN approach to synthesize the patient in different age. So for example, maybe our majority is from the younger patient, but we can use this approach, try to synthesize the patient in the older age. Then we can maybe make this database more balanced in the age.
And what is at the moment the best age to use this approach?
We didn't really come up the threshold, but I would say sometimes there are maybe older than 30 years old. Sometimes the prediction accuracy is not really comparable to the young generation.
Okay, thank you very much.
Thank you.
And to stay in time, we have to continue. Well, okay. The next presentation is given by Behnam Javanmardi. He's also from Bonn University Hospital, and we move now from the face to bone.
Good morning, everyone. It's a pleasure to present our work, Bone to Gene, to you. It's our effort here in Bonn at the IGSP to develop an AI or ML-based tool that would eventually recognize the features of different skeletal disorders based on X-ray imaging. I'm sure that for most of you an introduction is not necessary, but for the sake of completeness, I start with a few motivating slides with a disclosure that my background is physics, so I may not use the most proper terms when it comes to medical words. Although individually rare, however, collectively rare diseases affect a large number of people in the world. The estimated number of patients with only rare bone diseases is around 25 million in the world and around 2 million in the EU countries. I, for myself, would like to remind myself for whom and for what purpose we do this analysis. So I would like to also share with you the story I read from Christoph, who published his patient journey in the MPS and the website of the MPS Society. MPS is short for mucopolysaccharidosis. Christoph wrote that already from his youth he had problem with his hip and he couldn't make a fist with his hand, clearly showing that there was a problem with his hand. However, when he was a kid, the doctors told in his hometown, doctors told his mother that that's the way he is and he has to live with that. It wasn't until he was 30 years old that he was diagnosed by MPS type 1, at which point he was told that he has to immediately start enzyme replacement therapy if he wants to get to an advanced age. Christoph could be diagnosed much earlier. We all know that the patient's journey is not straightforward. They may have to visit up to 10 clinicians, get 2 to 3 misdiagnoses, and the process may take, on average, 5 to 7 years until an accurate diagnosis. For bone diseases, there are multiple information that goes into the solving of the puzzle of the diagnosis, and we know that looking at X-ray imaging is one of the main important ones, and in also molecular tests, because the majority of these diseases are genetic. And in addition, because many of these diseases have the symptom of abnormal growth, measuring the bone age is also another thing that clinicians do as one of the first steps into diagnosing of these diseases. However, there are more than 400 possible genes or disorders causing the phenotypes in a skeletal system, and experts cannot learn the features and patterns of all of them, and on top of that, experts cannot be everywhere. But AI or ML can learn the feature of any number of diseases if the data is available, and they're also not bound to a given geographic place. Currently, the most suitable, probably I've heard in different talks, the most suitable machine learning algorithm for analyzing of images and visual data is convolutional neural network, which is at the core of many computer vision tools already. And in simple words, what it does is that it runs a convolutional window on images, capturing the information of every pixel in the context of its surrounding pixels. And then by having multiple layers of convolution and a large number of parameters, it compares the prediction with the expectation, and it adjusts it until we have good performance. However, training a CNN, convolutional neural networks, needs a large number of data. So far, for our project, we have collected around 1,000 X-rays, but around 700, but exactly 771 images with confirmed, molecularly confirmed rare bone diseases that I list here. And this distribution shows also the different numbers for different diseases, and also based on sex, male and female. We have data from Ulrich Turner, Léry-Weill syndrome, Noonan, Silver-Russell, achondroplasia, hypochondroplasia, and pseudohypoparathyroidism. I'm not sure if you have already matched any of these diseases with these X-rays that I show. They are shown now. Probably the easiest one to diagnose, to see, is achondroplasia with shortening of fingers and trident hand features. But 800 or even 1,000 images are not enough for training a convolutional neural network from scratch. That's why we have to use a technique called transfer learning, which I come into. For that, we use the public data set of hand X-rays from the Radiological Society of North America that they published more than 12,000 hand X-rays with bone age. The data are from 2 hospitals in the US, and the bone age, or the weighted mean of 6 different experts, and based on the Grolish and Pilot standard. Here I'm showing you the distribution of bone age in this data set for the train, validation, and test set. The distributions are similar at different age ranges, and also for male and female. So what do we do in a transfer learning? before that, I must add that that was the reason we picked and we first started with the hand X-rays, because the images are few. We needed to do transfer learning, and their measuring of bone age is relatively routine at different hospitals. So there was a large number of hand X-rays that we could take for transfer learning. The first part is that we train a neural network that the image is an input and also the sex in the end, and the output is just bone age. First, the model is initialized by random parameters or random values. Then, after many epochs of training and back and forth and comparing with the expected result, we come to a state that the model is trained, therefore is performing as expected for assessing bone age. Then we just take this model, the main the part of the model, and replace the last layer, which was bone age, now with the different classes that we want the model to predict. At this stage, the model is not trained to do this classification of classes, but it also doesn't have to be trained from scratch. So from this point, we continue the training, and then we get to a stage of a trained model. That's the concept of transfer learning in a nutshell. We first have done the bone age training, and we have the AI that performs excellent on the reference public data set of RSNA with only a mean absolute difference, or MAD, of 3.9 months. This is prediction versus ground truth that was average of six experts. On average, experts or human graders perform with an MAD of 5 to 7 months. So the AI already is performing better on average than an average expert. More importantly, we took that AI model and tested it on the X-rays of the disorders that I showed you. The model hasn't seen any of these X-rays before, so it was served as an external test. And the MAD that we achieved for all the images, 771, was 7.5 with respect to just one grader. So we knew that if there is an also intergrader uncertainty, so we managed to get a second opinion for 568 of these X-rays, and the MAD already dropped to 5.8 months. We hope that we can get grades for the rest, and also maybe more than just 2, and we are sure that this performance would even be better. And we know that some of the existing tools for assessing bone age and currently available for clinicians fail to perform for some of these diseases, because the hand with some of these disorders is so dysmorphic that some of the conventional methods can't do that. I would like to open a parenthesis here to present an interesting finding that may not be useful clinically, and that is that its AI can detect or predict the sex of an individual based on only hand X-ray, something that surprised at least all the radiologists that I've talked to before this study. We know that the developmental phase of males and females are different at different ages, but completely different features wasn't known. This study, they also, their model predicts the male or female with 95% accuracy. Here they show a t-SNE plot of the last convolution layer that they show the males and females are clustered at different part of this space. Unfortunately, the image in the publication is not of high quality, but they also highlight the parts that the model looked at to make the decision. And they showed this, they did 2 experiments. First, 2 radiologists, accuracy for predicting sex was consistent with a random guess, around 50%. And the radiologist looked at those regions that the AI also has high attention, and they couldn't find any features different between male and female. We also just were interested to reproduce that. The first column shows our accuracy. We didn't push it. We are already at 93.4%. but then we tested that on the X-rays from different disorders, and for some of them the performance dropped significantly. I shouldn't and I don't want to overinterpret that, but this might hint towards an interesting point that there is a feature between male and female that the AI gets to learn about it and do the differentiation, and some of these disorders alters those features, and that's why the AI that performs 95% on normal hands cannot perform as well on the unhealthy hands. Going back to the main point, so we had the state-of-the-art performing bone age model, and then we took that and did the transfer learning that I explained to you to build a preliminary classifier for differentiation of different X-rays from different skeletal disorders. This is the result of the preliminary classifier that we have. It is, I'm here showing to you a confusion matrix. Does it work? Yeah, okay. The x-axis is the predicted class, the y-axis is the true class, and the diagonal of this matrix shows the accuracy of prediction per class. For example, achondroplasia 72%, and Ulrich Turner in the bottom right, just 27%. And the off-diagonal information is showing us how the model or AI is confusing different classes. For example, the model, I try to show this again, confuses or misclassifies 47% of pseudo-hypoparathyroidism as hypochondroplasia, or 41% of Ulrich Turner's 41% of, yes, Ulrich Turner is misclassified as Léry-Weill syndrome. So overall, we have an accuracy of 40%, average over all classes, and we know that out of 8 classes, random probability is just 200.5, so we are performing much better than random. It serves as a proof of concept, shows that we are on the right track, but we know that there are 2 points that influences the performance of any machine learning model and a classification. One is the number of data that you have per class, and another, in this case of images, how distinct the features of different classes are. And in fact, these confusion metrics can tell us about some of the similarities between different classes. For example, let's take hypochondroplasia and pseudo-hypoparathyroidism. They have many other different characteristic features too, but I picked the one that is the same between both, and that's brachydactyly. And that might be one, brachydactyly shortening of the fingers. That might be one feature that caused that confusion for ML, that dropped the performance for pseudo-hypoparathyroidism. Or for the other 2 that I showed you, Léry-Weill and Ulrich Turner syndrome. They also have shortening of 4th and 5th metacarpals, but they also have another feature in case of Léry-Weill syndrome, a pyramidization of the carpal row, and in case of Ulrich Turner syndrome, the angle that the triquetrum, lunate, and scaphoid made is smaller than normal, that is somehow similar to that pyramidization. So these phenotypic similarities can be the cause of confusion of the AI for different classes, and we know that by having a larger number of images per class, and also, as was shown in the Gestaltmacher study that Tzung told you about, if we have a larger number of classes, the performance of the model would definitely increase. I gradually move towards wrapping up. Bone2Gene will have 2 main modules. One of them is the bone age AI, and another one, disorder classifier. The bone age is already developed completely, and we are in the process of deploying it to the hospital for the use of clinicians, and the disorder classifier is under development. Eventually, it will be deployed as a web-based app that can be accessed anywhere, and the clinician can upload an X-ray and get both the bone age and the top N most probable disorder causing that phenotypic feature. You have heard about Gestalt Matcher. We are also in the Gestalt Matcher database collecting hand X-rays from different publications. You can contribute to that, but bulk of our data comes directly from unpublished cases, and from this is the network that we have so far established in Germany. The data are from 4 of these centers in Leipzig, Magdeburg, and here in Bonn. And we are, of course, interested to expand this network to a larger number of centers and also outside of Germany as well. This is the last slide. The main developer working on this project is Sebastian Rassmann, who is here. And you should check his poster number 5, in which he tells more details about the AI that he developed for the bone age assessment. And we have a website that at the moment contains the information that I told you about, but check it, the updates will come there. And thank you for your attention.
Yeah, thank you very much for this interesting talk. So there's a question over there, Ben.
Thanks, that was great. I actually have 2 very quick questions. First, just out of curiosity, not in the conditions you mentioned, but some other conditions, there can be asymmetry in the hands. So did you train on both hands? It looked like maybe just the left. That's the first question. And then the second question with Turner syndrome, I call it Turner, not Ulrich Turner, but often patients are a mosaic, there's some 45X and other components. So did you try to look or divide by karyotype? You might not have that information, but for the sex identification, that might show some differences there.
First, the second question, no, we haven't done that. First, we didn't go too much deep into the sex prediction yet. I mean, it was just like a side experiment we did. We also don't have that information, unfortunately. And yeah, it would be interesting to if we have that information, to also check that. For the first question, you're right. I think, if I'm not wrong, Noonan is also one of those that have Noonan syndrome, shows asymmetry in both hands. We haven't done that, unfortunately, either, for the main reason that we didn't have data so because assessing bone age is done mainly using the left hand X-ray, and that's what mainly different clinics and different hospitals have. Yeah, but that would be something to check if we have the data for sure. Thank you.
It was a great talk, by the way, just terrific.
Yeah.
Hi. Sorry. Great talk. I also read a recent paper in Lancet that said that for some reason AI was really good in predicting ethnicity in thoracic X-rays. So have you also tried to look into that? Maybe there's an error, and do you need more information to actually be able to do so?
To predict ethnicity?
So not to predict ethnicity, but to correct for ethnicity if it's needed.
Yeah, that was one thing that I didn't mention for the sake of time. We tested our bone age AI also on a data set that contained X-rays from different ethnicities. And the performance on because primarily the RSNA data that we trained the model on are from European backgrounds. So the non-European backgrounds or non-white ethnicities, the performance was a little less. That clearly shows that we need data from other ethnicities to remove this bias from the AI. But there are methods that we can do, and we are thinking and working on that. We can train the model to unlearn those features that basically picks based on ethnicity, and therefore performs better when it's and makes it more generalizable to other ethnicities.
I was thinking about your future plans. So what immediately came to my mind were also, we have many brain malformation syndromes. Are you planning to expand to that by something like brain to gene, or? We
are thinking about, and we were talking with Nikolas yesterday, and then about anything to gene, but sure, we really would like the bone-to-gene to be able to not work on just hand X-rays and all different X-rays of images of different body parts, but that of course requires data, and as I said, one reason that we picked hand X-rays was that this big data set was available, so we could do transfer learning. But for sure, we would like to, of course, expand it to other image modalities and body parts as well.
Right. Okay. Thank you. There's one last question over there. Could you please hand over the?
Here, I'm going to pass them.
Thank you.
So thanks a lot for this really cool presentation. It was super impressive. Maybe one question that also touches your direction a little about the future. At your first slide, you were showing that the family anamnesis, clinical information, biochemistry information, symptoms are also relevant for these rare bone diseases. Are you looking to include these into your models, or do you focus on the imaging part?
For now, we focus only on the imaging part, but that's something we know and we think about, but it's something, again, that looks like to be a little bit farther in the future than just now, because now we are at the stage of collecting X-ray, basically. And that brings me to the last thing I would like to say, that this is open to contribution, of course, and we are looking for data from different disorders, from different places. So if you're interested, please contact us.
Thank you very much.
Thank you.
So the next speaker is Nikolas Pontikos from the University College London, and we now move from bone to eye, and his talk is on eye to gene. The floor is yours.
Cool, thanks. Oh, it's all in German. Where's the slideshow? Presenter. Yeah. Oh, okay. Yeah, sorry. Makes sense. Thanks. Great. Thanks a lot for inviting me. This has been a really great conference so far. I've been really enjoying it. So yeah, I'm Nikolas. Pontikos. I managed to speak to a few of you already, but just introduce myself. I'm from UCL, University College London, specifically the Institute of Ophthalmology, and also from Moorfields Eye Hospital, which is a large specialist eye hospital in London. So I'm following up on the two really cool talks we just heard on face to gene and bone to gene. So I'm going to be talking to you about eye to gene. And don't worry, we're all talking to each other, and we are planning on all working together at some point, and maybe the Gestalt Matcher database would be a nice place to coordinate. So how can we use, how specifically, in eye to gene, we're looking at inherited retinal diseases, which are a type of monogenic disorders, and this is what I'm going to be talking to you about. So first, I'd like to start by telling you that imaging is really, really important in ophthalmology, in studying the eye. It's very easy to do. Anyone who's been to an eye hospital probably has had an eye image taken. You can obtain these really detailed 3D scans, which you're seeing here. So this is called an OCT scan, optical coherence tomography. And this is basically a 3D scan of the retina, which is at the back of the eye. So I think people probably have a basic knowledge about how vision works, but just to quickly reiterate, light comes in through here, it gets captured on the retina, and the retina basically feeds a signal to the optic nerve that directs it to the brain, and that's kind of like, high-level view of how vision works. Oh yeah, I should disclose I'm a computer scientist, by the way. So I have been working in eyes for a long time now, but I'm not a doctor. Yeah, as I said, images can be captured really easily, and there's a huge growing number of them, and this is just numbers from Moorfields Eye Hospital, where we've got, this is probably a huge underestimate, we've got many more now, I think, but basically since 2007, the number of scans has been growing rapidly. There's many types of imaging modalities. So what I mean by imaging modalities is basically different types of scanners that can use different light, for example, infrared or autofluorescence, and that can capture very detailed phenotypes of the eye. So here we've got different types of scanners. Here's the one by Heidelberg, which is very widely used, and this is the one which I will be presenting, talking about with I2Gene. And here are different types of images, so infrared, autofluorescence, and OCT. These are all types of images I'll be working on. There's many more, so there's possibilities for really expanding this scope. Yeah. So I mentioned I'm working on inherited retinal diseases. So these are, as you heard from face-to-gene and bone-to-gene, monogenic disorders as well. So if you've got a defect in a certain gene, then the chances are you will get the disease. We're not talking about common diseases here. These are like monogenic, highly penetrant diseases. And they have quite characteristic phenotypes. So here are just some images, and these are the genes which are linked, associated with that condition. So ABCA4, FMP1, H2A, choroideremia. What is interesting as well is some of these genes cause syndromes, and so that's why it's really interesting. Maybe if we can link this technology up to facial AI, or even maybe bone AI, or general more syndromic multi-organ AI. Over 270 genes have been found to be associated with inherited retinal diseases, so they are quite heterogeneous. And just to, kind of the schematic idea is that these genes, a lot of the genes are basically highly expressed in different cells of the retina. So this is just a schematic overview of the retina. Here you can see your cones and your rods, which probably most people know about. So these are the sort of really important photoreceptor cells. And there's quite a few genes which are really highly, expressed in these cells. And so depending on which cells are affected, this can explain why you see sort of very distinctive phenotypes. So identifying the gene which is associated with the disease is what we call is what I will be calling a genetic diagnosis. So I haven't got a nice map of the world to show how the prevalence of inherited retinal disease all over the world, which would be pretty cool to do. But I just have the numbers for the UK, which is where I've been working. So based on our estimates, we think there's around 30,000 inherited retinal disease patients. And as has been previously said, these are, although individually rare diseases, as a group, they are quite common, and especially in a certain demographic, younger people, they are like one of the leading causes of blindness in younger people. However, even, we've got really good phenotypes and everything, and we have in the UK a pretty well-developed genetic testing framework, which I'm going to be talking about. We still have like over a third of patients without a gene diagnosis. I imagine that in countries that do not have access to genetic testing, this is much higher. And in the UK, this is basically the cost of inherited retinal diseases. And it can take very long to get a genetic diagnosis because it's such a rare condition. Not many doctors have come across it. So the benefits of a timely genetic diagnosis, I'm kind of preaching to the choir here, but you all are familiar, I think, with benefits for family planning. For instance, if parents want to have a child, they need to know whether the chances of passing on their condition to their child. As I touched upon, the syndromic underlying conditions, which can be life-threatening. So, for example, Batten's disease is an example, which is a neurological condition, that is often manifests first in the eye. And also what's quite relevant for eyes is gene therapy, and that's really in development. And there's a few trials going on. There's already an approved treatment for RPE65, so Luxturna, you might have heard of. So that's really going to be a major driver for this project. And then, of course, for the healthcare system, knowing what's wrong with the patient is always very important and saves money. So in the UK, this is just an overview of how a genetic diagnosis might work. So I think one big difference with Germany, for example, is in the UK, opticians, so you're basically where you get your glasses, they actually take images of your eye. So they have some of these devices. They don't have the Heidelberg one I spoke about, but they have some other devices. So they basically, you can imagine that one of these 30,000 patients will eventually, get to an optician, and the optician might realize there's something wrong with the patient. And however, a lot of the time, they do a lot of false positive referrals, so they refer patients that actually don't have anything wrong, so that's another problem. And these patients will eventually, hopefully, be referred to a specialist eye hospital, like Moorfields, Manchester Eye Hospital is another one. And then eventually, we hope they'll get a gene test, and then a multidisciplinary team will be working on interpreting that data. So that will include a clinician, bioinformatician, geneticist, genetic counselor. They'll work together on trying to identify the gene diagnosis. So even after this process, even in a leading center for these types of diseases like Moorfields Eye Hospital, we also get less than 60% genetic diagnosis. So there are two kind of bottlenecks in the system. There's the referral one, which is very important, and there's genetic diagnosis one. The referral, we can use AI for these two to help us in these two types of approaches, or scenarios, I should say. However, it's very different types of AI systems we would need to develop. And the referral one would need to have access to real-world data from opticians, and it would be like more of a screening AI system where you'd have very low prevalence of, you'd expect very low prevalence of these rare diseases. The one we are focusing on, because we have access to the data in the hospitals, is the genetic diagnosis. So we have patients which have a suspected inherited retinal disease, and we are trying to make this system more efficient. So what we're developing is Eye2Gene, so an AI system that can take images from the different imaging modalities that I've mentioned, and can give you a report basically with a gene diagnosis, and ideally highlight as well the features in the retina which have been used for that gene diagnosis. So why is such a system important? Well, in the National Health Service, which is the healthcare system of in England, basically the type of genetic test you can do is determined by the doctor, and they have a website called the National Genomic Test Directory, where you go and there's basically a spreadsheet you download, and depending on what type of disease, it will tell you what type of test to do. So it can be either a single gene test, gene panel, or whole genome. It's moving much more now to whole genome, but for some conditions, still gene panel is offered. And the genetic testing happens, just for your interest, the genetic testing happens across these genomic laboratory hubs. That's how the England region is split. There's 7 hubs in total. So as I mentioned, whole genome sequencing is now much more available in the NHS, and in particular for rare disease patients and cancer patients. So you might have heard of Genomics England, 100,000 genomes. So these are some results that you can go and see yourself on their dashboard. So they've basically sequenced that many patients in total, of which that many, 3,000, are basically rare eye disease patients. And here is the breakdown the breakdown of the different types of, a more sort of a fine-grained breakdown of the different types of diseases. So posterior segment abnormalities, they're using HPO terms here. So these are, this is a fancy way of just saying kind of retinal conditions mostly. So I think one thing to take from this is that rare eye diseases are quite well represented in Genomics England. They've published their pilot paper where they show the sort of gene diagnosis yield. And yeah, so I'm sure everyone's here, or people working in this area have read this paper, but basically the sort of take-home message is that, you know, the number of the diagnostic yield is not that high. You know, this is two take-home measures. Actually, firstly, the diagnostic yield is not that high, and in the ones where the diagnostic was successful, there was a gene diagnosis, automated pipelines were really efficient at doing so. So although the overall diagnostic yield is pretty low at 25%, ophthalmology is doing pretty well within Genomics England, but it's still less than 50%. So, you know, we should be doing better. And this is where we think, for example, eye to gene and better variant interpretation can help. So the type of variant interpretation that has been done in Genomics England is using Exomizer, which is developed, I think, Peter's been part of the team, using the human phenotype ontology terms, so basically text descriptions of phenotypes, and these have been fed along with genetics variants information, and this is being used basically to score variants. So where we would like to fit eye to gene is similar to the PDA approach with face to gene, is to basically use it to help to provide an additional scoring for variant prioritization, and also like the work of Alex Hustings to maybe use it directly to get HPO terms out. So yeah. I should say, you know, it's obvious that, you know, face to gene has been a big inspiration for us. So these are our current goals with the eye to gene project. So number one, to guide genetic test prescription, and two, to guide the genetic variant interpretation. And by doing both of these things, we hope to accelerate the genetic diagnosis. So I'm halfway through, and that was basically the background. Now I'm just going to talk about the eye to gene technology. So we trained it on the Moorfields inherited retinal disease data set, and we are in a lucky position that we have a big, quite large data set of inherited retinal diseases. I think one of the largest in the world, and a single center at least. And these are the numbers that we've got of the different types of imaging modalities. And this is just an illustration of the different types of images. Here you've got the different genes. First thing you'll notice is, again, this problem of class imbalance, which plagues all of us in rare diseases. So a huge representation of ABCA4, also known as Stargardt disease, followed by a few retinitis pigmentosa genes, of which USH2A is the second most common. And then you've got your very much rarer genes, and the one that has a gene therapy, RP65, is here. So, but yeah, we're hoping we'll get more treatments. RPGR, there's a phase, I think it's phase 2, can't remember. Anyway, there's a trial definitely in RPGR. It's coming to end, probably phase 3 even. So we've used this data set of 36 genes and 1,907 IRD patients, in total of 40,000 images to train eye to gene. So the approach is this sort of what we call, you know, multimodal imaging kind of approach, where we basically train a classifier on each of the imaging modalities, and combine these to provide a ensemble prediction. So we've used Inception v3, and what we've done also is we've done a sort of five-fold cross-validation approach. So we've split our data set up. And one of the good things of doing that is it gives us some sort of idea of uncertainty, because we can use the different model predictions to give you some variance in the predictions. And also the sampling approach can also help with getting a different gene distribution, which is something which is important when you want to generalize to a different population where the gene distribution might be different. So in total, we basically get 15 networks, which we ensembled. So five networks per modality, 3 modalities, 15 in total, and we get we've combined the 3 models into the IT gene. Sorry. So we've validated IT gene on our internal validation data set, and this is with Prof. Michel Michaelides. And this was an internal data set, which was obviously distinct from our training data set. And I don't need to explain what top 1 and top 5 accuracy is, because Behnam explained it, or Face the Gene explained it. But anyway, yeah, so that's the idea. And yeah, this is what the gene distribution looks like in our test data set. So I think that's important to bear in mind that, if your gene distribution is different, then you won't expect same quality of results. So this is the confusion matrix. It's quite small, but so you probably can't read it very well. But one take-home message is that if you look at the underlying gene count versus the predicted gene count, we've tended to kind of overpredict common genes, and underpredict rare genes. Because we're using these 3 different imaging modalities, we can also look at how we can look at the individual gene classifications and see how well each image modality does for a specific gene. And so here you've got your 36 genes. The different colors here are the different imaging modalities. So in blue, you've got FAF, in red, IR, and in green, OCT. And what you can see is, for most of the genes, it's not making a very big difference. However, you do see some separation, for example, for CRB1. And CRB1 is, this kind of makes sense, because CRB1 is distinct by its thickening of the retina. And this can be seen quite clearly on OCT, but not so much on the FAS imaging that you get with autofluorescence and infrared. We've obviously, internal validation is good, but what the real gold standard is external validation. And so thanks to Frank Holtz and his team, we've managed to externally validate it on the Bonn dataset. And also, as part of our collaboration on IT gene, Oxford and Liverpool have basically shared their data with us, and we've been able to validate it as well. So what we see from here is we see that we'd expect a drop in the performance, but it's still pretty decent, especially in terms of the top 5 prediction. And yes, we also managed to get a small data set from Sao Paulo, from Brazil. Obviously, we always want to get more data. That's the key. And yeah, and again, as Behnam mentioned, when people see 50%, they think, okay, that's not very good. But if you think that you're classifying between 36, then it's pretty good, much better than random. We're also interested in comparing this to human experts, ophthalmologists who are specialists in these types of diseases. So we gave them a little quiz. So we basically gave them unlabeled images and specifically autofluorescence scans, which they should be quite familiar with. And we asked them to predict what is the gene. So in the human benchmark experiment, their top 5 accuracy was 36, and the combined top 5, so this is being very friendly, and basically if anyone gets it right, it counts as a right guess, is 78. And the in comparison, I2Gene just on that data set achieves top 5 of 72, so much better. This was touched upon in the previous talks, that the age of the patient is really important when you do the gene diagnosis. And this is just a heat map showing here the genes, and at the bottom the ages of the patients. So what you see is that some patients present much earlier, and obviously we have to be a bit careful about this because there might be some reasons why that is the case. The patient might be seen in a different hospital because there might be a syndromic patient, for example. But this is still useful information for us, and so we can try and incorporate this. And also the mode of inheritance, if known. Most of the time it's not known, so it's not. Well, actually, that's not true. If it's a child, the parents are there, and sometimes they have some idea. If it's an adult, it's harder to get at. But yeah, that can be helpful, not for genes which are both obviously dominant and can be both dominant and recessive, but more for, like, I guess, the X-linked genes that is useful information. And so I'm aware this is moving beyond imaging, but I think this is still important information to try and incorporate, because as Behnam had this puzzle figure, this is just another piece of the puzzle in the gene diagnosis. And we did the experiment to see basically if age by itself, mode inheritance in orange, and so if it's, I can't even see it myself yet, I2Gene by itself in green and combined in red. And what we do see is that, for example, for the X-linked genes in particular, it's helping quite a bit. For example, RS1 and RPGR, as you can see here. And here's the table of the results. Yeah, it does help. Here's the take-home message. So it's worth incorporating this information. Finally, in the final stretch here, again, recurring theme, the challenge of small data sets and imbalanced data sets. Here's our accuracy, and here's how frequent the genes are in our data set. If you get a higher frequency, you do better. The classifier does better. How do we work around this problem? Ideally, more data, but we've also tried, like the Face2Gene team, we've also tried a synthetic data approach. So this is work by Advaith, working with me. And basically, these are image examples here. Each row is a synthetic generated retina. And we're using a StarGAN2 approach, which I think we'll be hearing more about later today. So this is like synthetic images, and this is the latent space, which we've heard about yesterday as well in the first talk. Sorry, I forgot the name of the speaker. But yeah, that's the idea of, and also in the previous talks of Face2Gene about the feature space. And we see that the real and the synthetic kind of cluster in the same space, which is okay, good. And then we can kind of use this, what's pretty cool is we can sample this feature space to go from different types within a class, for example, to look at within the ABCO4 class, or to go between classes. We haven't really found the utility for this, but it's a cool utilization. But I think what Face2Gene is doing, Gestalt Matcher, is really cool. So that's definitely like something we should be looking at as well. And I think there's a poster as well, right, on, yeah, more specifically on generating synthetic faces, which I'm going to have a look at more in detail later. So what we were trying to do with that was basically see if we could augment our training data set to get better performance. And basically what we've tried to do is combine the data in different ways with real data. So either by just adding more synthetic data to our data. So we've done this in different kind of regimes. So regime 1, we basically use 100% of the data. And we use the StarGAN2 to generate it, and then we do augmentation. Here, obviously, we're adding, from the same data source, so it's probably not going to improve things much. Here, we're trying to put just synthetic data in, and here is a scenario where you have a smaller amount of data, basically. So we did this, and a bit disappointedly, we didn't find really much improvement in the classifier, which might be expected if the GANs are not really providing new information. But I think talking to Peter and people in his team yesterday, they've had more success. So I'm interested in discussing that. It might be, you know, I think it's not a nail in the coffin kind of thing, but it's worth investigating. One thing that was interesting, though, is that just using the synthetic data was giving us similar classification and accuracy to using the real data. So that's quite interesting for the privacy purposes, potentially, as long as the synthetic data is sufficiently different from the real data, which we, from our experiments, it looks like it is, but that's still, you know, up for debate. And then what we're doing now, final slide, is basically trying another approach, which, you know, is for explainability, which is basically looking at the retinal features, and we're hoping this can maybe help as well with the classification of the rarer genes, if we can find some very specific features in the rarer genes. So this is work by William, my postdoc in my team, and with collaborators at Moorfields. So to conclude, I2 gene is predicting the 36 most common IRD genes with an accuracy of at least 75%. Performance is similar and even better to human experts. However, we still need to increase our data set. We need to improve the AI interpretability. One important point is disease stage, which was mentioned in both previous talks. And we need to try and predict more classes. This is where maybe the Gestalt match approach would be very useful. And we're hoping, obviously, to make it widely available. Check out our website. It's quite nice. We've made it like patient-friendly, and there's also an app there. You can upload scans. We haven't made that open to everyone because we don't want anyone using it at the moment, getting complaints of gene diagnosis. Thanks everyone for here. You know, specific thanks to Peter Kravitz, Frank Holtz, Behnam, everyone in the team. I didn't get a chance to talk about our nice work with fundus to gender. I thought I should have mentioned that as well, but we can talk about it later. Yeah, thanks everyone at Moorfields, UCL, etc.
Yeah, thank you very much for this really great talk. Particularly in this field of eye diseases, we are, as you mentioned, are moving to gene therapies, so an early diagnosis is really crucial, and it's great to have such tools. So my question would be, especially in your field, you have also the possibility to include longitudinal data because the patient come annually and you do the scans over time. So are you already implementing this into I2 gene, because this could also help to improve the diagnostic yield and the guesses?
Yeah, absolutely. So just the age at presentation for now,
yeah,
which is the age at first presentation.
Yeah.
But you're absolutely right that looking at the progression is really important. So yeah, that's you know in the plan, but that's not part of the results I showed today. We're just mixing all the ages in at the moment. But I think we can get much better performance if we use such an approach. Yeah.
Thank you.
Thank you, Niklas, for the brilliant talk. And I think you successfully develop a tool that is really much needed in the clinical space of inherited retinal diseases. Just two questions coming up. You showed very nice and crisp, clear images, and we know that sometimes image quality may be suboptimal. Could be due to media opacities or patients with cooperation issues, and some of these younger patients have nystagmus where the eye wobbles all the time. So how would this impact the performance of your automated pipeline? And secondly, the image frame is restricted of the devices. Do you think there would be a higher yield with going to wide field imaging systems?
Yeah, great. Thanks a lot, Frank. I didn't see you there, so yeah, it's great. I'm glad you attended. Great questions. Yeah, your last question, which was about wide field, absolutely, that's really interesting. And in the UK we have Optos, I don't know if it's something you use a lot here, the Optos device. So that would be quite interesting to incorporate that. I think it's more challenging data set because just the imaging is less standardized. But I think there maybe a segmentation kind of approach would be quite nice, just because there's so much other stuff happening in the image that could confuse a sort of classifier system. So I think that's really interesting, and that's definitely like a spin out that we should be exploring. And your first question, which was on image quality, very important. And at the moment, we have basic thresholds for image quality. And these are based on like some numeric values. We use the BRIS score, which Behnam had recommended to us actually. And also some other pixel noise metrics, intensity of the image, things like this. But yeah, there's always going to be cases where the image quality is not going to be good. And then I think that's where the network uncertainty is really important, to know whether or not we should be taking another image or whether we should be using that image for the diagnosis. Yeah, but sometimes image quality is also part of the helps for the diagnosis in a way, because it's underlying, as you mentioned, nystagmus, for example. That's additional information. So, but you probably don't want to use that in your classifier, I'm guessing, because it's more of a confounder than yeah. But yeah, thanks a lot, Frank.
Okay, one last question.
Quick question, great talk. So because of kind of the inherent characteristic of this disease, do you also, once you have identified a patient, also focus on the close family members? And also, this could also be an idea to kind of study penetrance, for example, or even like better your model as it is.
So you're suggesting incorporating relatives' images into the diagnosis? Yeah. 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 A great idea, and definitely, I think something anyone who works in this disease space of rare diseases should try and, I think, incorporate other images. But I guess it depends on the, so the status of those individuals, if they're affected or not. Is that?
So you know that one individual of this family is affected. So this is also something that we do in IBD a lot. Because
so you want to find out if other relatives are affected?
Mm-hmm.
Okay. I thought you were using that as, like, you were using unaffected individuals, for example, to...
unaffected of the same family, kind of. That's the idea.
Yeah.
Also to kind of better...
For training the system, or for predict... Okay, but anyway, for predicting, definitely, yes, important. And I think good to do, but also a good idea is maybe for training the system as well, if you can incorporate information from other relatives. Yeah, but obviously, it's always important to know if somebody else, if it's, depending on the onset of a disease, if unaffected individual is, much older and hasn't had the disease, for example, you kind of know that they're not going to get it. But sometimes you might have younger individuals that are, I guess, earlier stages of the disease, so that can be useful information. It goes back to your point of the disease progression. So yeah, it's not a very yeah. It's I think there's a lot to think about how that can be incorporated in different ways. Yeah.
Happy to talk.
Yeah, happy to talk as well. Thanks.
So, Nikolas, thank you very much again.
Thanks a lot.
So last but not least, we have Jan Kirchhoff from Medical Values here, and happy to hear your talk.
If you want to use the pointer, you can also attach it.
I think that's okay. There we go. I think that's fine. Yeah, so it's always tough to be in between the lunch break and the last talks, especially since you've already seen very impressive presentations. I think in my presentation I will touch a couple of points. So yesterday and today we have seen that oftentimes there is a diagnostic pathway starting from a family physician all the way to reaching the expert, for example, here in the university hospital. And one thing we also heard in every AI talk was the topic of having too few data sets, and this is the second part around data enrichment that I will cover. One or two sentences about myself. I'm one of the two founders of Medical Values. We are a team of physicians, data scientists, and engineers from Karlsruhe. Growing quite quickly, about 20 people to 30. And what I will cover today is, first of all, why does it matter to deal with diagnostic pathways? As a startup, it's also important to touch the economic points or why it makes sense. And then I will discuss a little bit of technology and then dive into data standardization and fairness. So to start with the motivation, why does it make sense to deal with diagnostic pathways and making life simpler? So there is a couple of German words in here, but I made the genetics piece a little bit bigger. This is from one of our partners like Unilabs. When you go on their website, maybe not right now, maybe later, you will figure out that they have a huge database of genetic testing that you can search through, which of course makes it very difficult for family physicians to actually understand what to select. And even in the, let's say, standard lab medicine, you can download it even as a book or order it, and it has like 590 pages. So I'm bringing this up because the diagnostic power or diagnostic potential is huge, but it's already now overwhelming. And with all the research happening by teams like yours, it's getting even more complex for the family physician, but also the physician working in hospitals. Another motivation besides this complexity issue is something we hear especially from younger physicians, that you have an experience at home. We also heard yesterday a great talk about the B2C-like consumer experience, and then you got to work with your hospital systems and your experience is quite different. So there's really a shift in expectation. What we do as a company is working on turning data points into actionable insights. So unfortunately, we are not a research company. We are involved in some research, but for us, it's really about deriving actionable insights to make the very busy life of physicians, hospitals, and residential physicians easier. So we not just digitize a report, but really turn it into actionable insights, recommendations. Already mentioned that there is all kinds of new knowledge being added every day to the medical research world. There is tests coming from Illumina, from Siemens, from Roche, from all the large companies. But what we would like to address is this unused potential between the routine diagnostic happening nowadays and what could be possible. To put some numbers behind that, there are studies that around about 20% of tests are unnecessary, double testing that happens, but also 45% is indicated that another test should have been done, but was not done by a physician. So these are huge numbers, and we would like to close this gap a little bit. Another issue, which is probably interesting here in this audience, that we experience a lot, that also among large laboratory chains, there's the routine diagnostic piece that processes like 20,000 lab tests a day in one center, and then they've bought the genetics testing centers. But often there's really a disconnect, although the diagnostic pathway actually starts with routine testing with a family physician and then goes all the way to the specialized center. So it's really about connecting these two. And the last slide around the motivation, we heard a lot about the tech giants also in the talks the last days. And what I think is interesting, when you go on the Apple website, they also share lab results. But what's interesting, it's actually just a piece of paper on your iPhone. So for a physician or for a private person, seeing your cholesterol without any interpretation maybe is also not very helpful. So we address these issues with diagnostic pathways and AI. And what's important in this space, and this is like our big vision we are working on, is to combine lab tests, symptoms, demographic data, also family analysis, we hear it right now, imaging data, and then also genomics data into one comprehensive solution, and then deliver solutions that help physicians in their daily life. We mainly work with laboratories and clinics like the University Hospital in Mannheim and Marburg, but also large laboratories like Amedes, for example. And what is interesting when we are doing our projects is that oftentimes at some point you reach the point where it often addresses also the general practitioner. So for example, in rheumatology, or even we had discussions around rare diseases, it's often the family practitioner who has the chance that she can guide the patient to the right specialist, and oftentimes that is where the issue raises and why it takes so long to get to the right diagnosis. So having an AI-based decision support system, in our experience, is also very helpful the earlier you can apply it and to get it in the hands of general practitioners. Another piece, and there's all kinds of funny images you can select about providing data in context. And this is something that I thought was very interesting in the discussions we heard in the last days, that there's the genetics testing, there's the imaging, but oftentimes it's also very interesting for a physician to have other insights about the patient, like symptoms, medicine the patient takes, and all of these data points. And this is less of an AI problem, but also a problem of aligning processes to actually get the data and the data points to the right experts. So to make a classic example, you have a very well-trained, high-paid physician working in a lab or a genetics expert, but then there is just the information, a 30-year-old woman on the lab test. So there could be a whole lot of better information, better diagnostic recommendation be done by the expert if he or she would get some clinical relevant information and not just the 2 data points and the measurements from the machine. So to dive a little bit in the AI side, we have heard a lot about specialized solutions, very impressive eye-to-gene, bone-to-gene. We rather take a relatively broad approach. So we focus on like endocrinology, infectiology, but even in the space of oncology, it's very important to also understand and connect related diseases like your digestion that is impacted. So we are not going into the deep dive, so we are very happy to connect to systems like eye-to-gene, but we rather try to connect on a relatively broad perspective the data points. And in practice, this is what the physicians in our team use, but what also external physicians started adopting, as it's a very graphical way. This is our knowledge graph editor, and you can see here, for example, in this androgen syndrome, that you really have clinical analysis, you have genetic analysis, the routine lab, and radiology information. And what's important is that we really work with the hospitals. In other countries, it's sometimes a little bit simpler than in Germany to also get these data points in a digital format. After that, on our platform that we deploy decentral, we also heavily focus on understanding the correlations between symptoms, ethnicity, age, imaging data, lab test data, because we really see the performance of the models improving massively when you can combine those different data points into one model. And one point is also interesting, the idea of a white box AI. Although in practice, we always try to do it as good as possible, but sometimes when you have a residential physician who sees 30 to 50 patients every morning, of course you can offer him the option to explain the model of what happened, but often he or she just says, let's keep it very simple, I need the action and insights. It's interesting that you can explain it, but I don't have the time. Maybe one point around motivation here. It's also an interesting slide because we were talking a lot about imaging data again this morning. This is from Nature, and you also see here that radiology is always one of the really leading examples in terms of the FDA approval. In my opinion, and I've worked, for example, before that at SAP, there's a lot of AI projects starting in the machine learning space with imaging because it's like a really tangible topic. It's very nice to look at these results. But in the business world, oftentimes it was more on the boring side of data, like some old SAP data that made Celonis now a 10 billion company. So maybe as a motivation, imaging is cool, but there's also the rather boring standard data that often have a lot of value. Maybe one sentence for you to also better understand the idea how we approach this data and the information we need in order to train such multimodal medical algorithms. So we basically take a three-step approach. We first create this knowledge graph based on good medical practice, based on up-to-date literature that we basically model. Then we take medical data from different facilities, also in decentralized approach, like we heard yesterday. So here we work, for example, with the Rheuma 38 Research Center, with cancer centers where we really train, but also then for specific disease area. And one part, and that's the last one, which is very interesting, is to integrate a feedback loop. So, for example, in the space of test ordering, we provide a recommendation, and then we actually see, okay, does the physician follow this recommendation or does she neglect it? And this gives us a really good insight and an idea how good our recommendations are. So this kind of three-layered approach really helps reducing a little bit this pure dependency on large training data sets. Coming to the last topic before also showing a little bit of a live demo, there is the one part data standardization, large data sets, and then also the idea of fairness. And to make this point of fairness a little bit more tangible, so we have one project to show one extreme in the space of oncology. Here they are talking about a large data set with 200 patients recovered, and it has also around about 200 input factors. So here we had to pay an oncologist, a radiologist, and a laboratory physician to handcraft this really small data set. So that's the oncology space. Complex diagnostic pathway, very expensive to get training data. On the other hand, you have diseases like an anemia. Here, a residential lab can give you 100,000 test data sets if you want it. It's this very few input factors, and you can use the hemoglobin level as your labeling parameter. So these are two extremes, and the bad thing is actually that the more complex the algorithm, the more training data you need, but also the more difficult it is to get to the training data. So it's a very tricky situation you're in, especially when it comes to complex disease areas or rare diseases. One way to address this topic, and sorry to bother you on a Friday with such boring issues, but it's really about data standardization. So for example, the SNOMED coding, REDLEX for imaging or LOIN coding is super important so that the data sets are actually comparable, so that you understand how has it been measured, what does it actually say. This really makes life a lot easier. And here on this side, we also help our customers with such mapping tools, because it's the typical work of a data scientist. Oftentimes, it's really a lot about standards, cleaning data, and not so much about the fancy AI topics. After coming to this relatively boring piece, now a little bit more interesting on the fairness in AI, because one of the topics here is blockchain. And in this space, also building on this issue of data sets, it's interesting that you might have one clinic that might have a relatively large data set for one disease area and another clinic for another disease area. And what I see a lot of times happening in research is that there's kind of a disconnect. There's one group training for that, one group training for that, but the patients actually, there's also diabetes patients in clinic B, so you somehow need to make or create a fair way to make this available. And we've worked with the Karlsruhe Institute of Technology on basically addressing this issue and coming up with an idea how you can actually pay somebody for providing data and then have an incentivation when you use the data for your predictions. So that was kind of the approach. And the idea really is here that there is an incentivation to provide labeled data, standardized data, so that you can get a payout also for other disease areas. And before we dive into the live demo, maybe one little bit of background for what you're going to see now. As I've tried to explain beforehand, it makes a huge difference for creating such models if it's just a lot of data. This is what many residential labs can really provide us, or if you have labeled data that use standards, that has a good gender distribution, that has an age distribution. So there's really a difference, so to say, in the value of data sets. And what we implemented with also working together with the university is a relatively simple algorithm that makes it relatively easy for physicians to understand the value of the data sets they provide. And jumping into a live demo here, basically what you hopefully can see. Oh, there we go. What you can see here basically is this landing page. You can log in and then connect to your MetaMask or whatever you want to use. But for the sake of demonstration, I had a colleague of mine mock these information. And basically the idea would be here that we have 4 hospitals that are all connected to this blockchain-based system. And then you can set up different budgets for your disease in something we call Medicoin, so some kind of value that you assign. So you might say COVID-19 has a 5,000 as an incentive, and influenza only 500 or whatever you want to add. And then the idea is that one user or hospital in this case could input data. And of course, we would analyze this data set, but you can put in here, for example, 200 patients, number of attributes. And now, of course, the data would be processed locally. The information would be sent. And basically, the trick is now that we calculate the value. You see your budget that we assigned. And then we can confirm our contribution. And what basically, hopefully it works. So now this user got as an incentive 250 Medicoins in our fictional area. This is being redistributed, decentralized to the other users. It's basically locked in the blockchain that somebody transferred these 250 Medicoins. And if we now use the user 2, we will also do the same idea here. Leave everything else empty, confirm the contribution, and you've seen that I basically didn't change anything, but the idea would be here, if you basically add now more data sets for the same one, the reward basically gets a little bit lower. We even experimented, as it has become quite popular, with some kind of inflation. So we try to make it as realistic as possible. But now this basically contributor for contributing the same data set would only get 237 Medicoins, because we already have some data for this disease. We might want something for different data. And then the other thing we often show then when demoing this solution is that we can say, of course, here you can add more users. You can say age data is available. You might have invalid age information, gender data available, SNOMED coins, empty fields. So this is basically what I'm mocking here. This is what our algorithms that's stored on the blockchain would basically do in the background to look at the data input, do this processing. But this is the idea that you basically can show to a physician or to a researcher that not all data sets are created equal, and that it makes a huge difference if you have such standards in place. And here we also get now a whole lot of more Medicoins for our wonderful contribution. And on the blockchain, we can see that the different contributions are added. So to sum up this idea here, this is one way of basically using the blockchain and such a coin to create more transparency and also create incentives for sharing labeled and valuable data to have enough training data sets for the great applications we've seen. All right, and we have 3 minutes left until the coffee break, so I hope I can also still answer some questions. And I'm also outdoors if you want to discuss something in more details.
Yeah, thank you very much. Are there questions from the audience? Over there, please.
Thank you. All right, really nice talk. What I was wondering actually is the data is already de-identified at the hospitals, right? Before sending to the other clinics or sharing the data. Now, what I was wondering is what happens if a patient visits not one hospital, but rather different hospitals, and they would basically share the data, but the patient is now duplicated in some way because the other hospitals will probably not know that the same patient was evaluated probably with similar techniques, so similar data is generated. So how can you avoid this kind of data duplication due to patients visiting several hospitals?
Okay, first of all, a really cool question. So in this setup, the way we've built it was actually for a decentralized learning approach. So we actually only share the information about the value of the data set, but the data set was staying in the hospital itself. So we did not centralize the data sets. It was just what we centralized was, or setting up was this coins and distributing them. So maybe that is the first answer, that no data was shared in this setup. The other point about the patient visiting the same hospital at the same time, it could be done with one patient, but one thing we discussed a lot was hospitals cheating. Basically, hospitals uploading the same data sets and just manipulating it a little bit, or it's kind of the same effect like having one patient visiting different hospitals. And basically the way we would have done it here, but this was not yet implemented, is that we looked at, okay, how big is the impact of the data set on the quality of the algorithms? Because then you could say, okay, it looks like, okay, you uploaded a new data set, but it didn't really improve the performance of the model, so there is no real reward. So that would be one way to avoid cheating and basically using the same data or the same patient a couple of times.
Thank you, and I think that's really interesting. Also, I think the technique which you just suggested may also motivate clinics from like different locations with like a totally different set of patients to basically provide their data, because their reward will probably be higher compared to like clinics in the same city or whatever, where the patient pool is very similar.
Absolutely, and we see that we work, for example, with a lab in Nairobi in Kenya, different ethnicity, different reference ranges, so it's very important to have these variability, whereas what you often see in research setups, it's oftentimes that they cluster in one regional area where you have a lot of similar patients. Yeah.
Thank you.
Okay, so thank you very much, Jan. You can also visit him outside at his booth, as he said. Thanks to all the 4 speakers for this session, for giving their presentations.